Welcome to AP Chemistry at Huntington High School. I'm BBrown, and today we'll be looking at the Chapter 6, 7, 21 test and some of the misconceptions and problems that people have. So there's a number of different things I really want to look at in our discussion today. So there's about 9 different things I want to highlight that I've seen students struggle with or have misconceptions about. Now the first one we're going to look at, remember, same as every single test. Watch your units, watch your units, watch your units. In particular, one that throws people is joules. Remember, if you ever see joules anywhere, it locks you into kilograms and meters and seconds. And remember, things like um, the energy equation, Planck's constant, has joule seconds in it. So that also locks us into joules. So when you see H, that's locking us into joules. That's locking us into kilogram, meters, and seconds. So be careful of that. Also remember, for the energy equation, so energy equals H times the frequency. Remember when you're doing this, this is the amount of energy for one photon. So we're dealing with one photon where we use that equation. So that's one thing to watch out for. Another common misconception are the relationships between n, l, and m sub l are quantum number type stuff. Remember, n can technically be any integer, 1, 2, 3, or greater. We normally deal with 1 through 7 because our ground state viable elements only have that many electrons, but technically there's the 8th energy level, ninth, and so on. A couple of relationships to remember about n. Remember, n squared always gives you the number of orbitals on a level. So on the first level, you've got the s orbital and that's it. So 1 squared would be 1. So second level, 2 squared is 4. We have your 1s and your 3p's for a total of 4. And then how many electrons would it take to fill all of those? So that would be 2n squared because each orbital can hold 2. So that's a couple of relationships to remember. L, this is always one that throws people. Remember, L is the shape, and that's 0, 1, 2, 3. And the way to think about this is shape. Remember, that's the number for S, that's the number for P, the number for D, and the number for F. So if you think of it through shape, as you learned it last year, it makes it a little bit easier. And remember, L is related to N. The maximum L value you can have on any energy level would be N minus 1. So on the third energy level, our maximum L value is 2. So we can have our 0, 1, and 2, our S, P, and D. And then don't forget M sub L is also related to a previous idea. M sub L is orientation. So which particular orbital on the entire sublevel, which orientation of my P or D or F, because remember there's only one orientation for an S. And we number those things from negative L up to positive L. Why? Because it gives us the right number. So if we're in the L equals 2, that would be a D sublevel. The 5 orbitals would be negative 2, negative 1, 0, 1, and 2. So if I go to negative L to positive L, that gives me the right number of possible orientations. So those are some relationships between NL and M sub L. Know your electron configuration rules, Aufbau, Hund's rule, Pauli exclusion principle. Aufbau, remember, is lowest energy first. Your block periodic table is the easiest way to see what comes next. Hund's rule on an equal energy sublevel, so on a P, a D, or an F on any energy level, each orbital must have 1 before any orbital gets a second. It's all about lower energy and the fact that when you cram a second one in, you've got greater electron repulsion. That's going to be higher energy, less stable, so you put 1 in each. And then Pauli exclusion principle, no 2 electrons can have the same 4 quantum numbers. And remember that fundamentally means in an orbital, you can't have up, up. That's really what that comes down to. It's got to be up, down so that you have 4 unique quantum numbers. And remember, 2 quantum numbers defines a sublevel, and 3 quantum numbers defines an orbital. 4 quantum numbers define the exact electron. Number 4, recognize ground state versus excited state. So if you have this electron configuration, would that be a ground state or an excited state? So 1s2, 2s2, 2p5, 3s1. Remember, by Aufbau, it should look like this. I mean, it's 10 electrons if you add them all up. So remember, add up all of your subs or superscripts here, and that'll tell you how many electrons, and then you know what substance. Well, neon is supposed to be 1s2, 2s2. Oops. I was supposed to cut and paste that. So what this is supposed to be is 1s2, 2s2, 2p6. That's what neon's supposed to be. So if it's 2p5, 3s1, then we've promoted one of these p electrons up to a higher level s, and that's going to give us then Instead of 6 in that P, we're only going to have 5, and that one got promoted up one, so it's going to be that. Remember, this could have been anything. I mean, I could have jumped it up to the ninth level S. That's still going to be an excited state, not ground state situation. So it's ground state, not excited state, because it really, 10 electrons is neon. That should be 1s2, 2s2, 2p6. Next, writing electron configurations after ionizations occur, and know when atoms are going to have, what it means to have a large jump in ionization energy, and for a particular atom, where that's going to occur. So first off, writing electron configuration after ionization. Now remember, an ionization means to remove one electron. So what that would look like as a reaction for Mg would be it's making Mg plus an electron. That would be the first ionization of magnesium. Now, what happens to the electron configurations? Well, remember, magnesium is neon 3s2. If we've taken away an electron, it's got to come from somewhere, or the only place we can pull from here, because we're pulling from the outside, remember the order is first pull from the P, then pull from the S, and then pull from the D. Well, all we have is the S. So that's going to become neon 3s1. Now, if we underwent another ionization, then we would be down to neon. So if we went through another ionization, we would end up with Mg2 plus. That's what the reaction would look like for the next one. And that would end up giving us neon. Now, once you've got neon, remember that's really, if you're looking at the periodic table, that's 1s2, 2s2, 2p6. Now, if I'm pulling out another electron, I'm not pulling from the third level, I'm pulling from the second level. When you're close to the nucleus has a much greater hold on you, so it's going to take a lot more energy to pull it out. That's why we see that massive jump, and that's why we stop right here, I should say, at Mg2 plus, and we don't go one more. So to take out a third electron, to go through a third ionization, is going to be very difficult, because once we get through 2 ionizations, now we're on the second energy level and the third energy level, and with that lower end, the electron is much closer to the nucleus. Nucleus has a much greater hold on it, much, much harder to pull out. So huge jump in ionization energy. Next, know why all trends occur. I've tried to hound and hammer this in. Period trends are all caused by increasing effective nuclear charge, and then what that means for whatever trend you're looking at. And group trend always start with increasing n. Increasing n greater distance. Those are the two ideas. So increasing n causes greater distance from the nucleus, which causes dot, 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 whatever then happens after that. Know those cold. What state are ionic compounds and molecules found? This is a common question because it's something people don't think about. Remember, one of the differences with AP chemistry is we go so many other places besides just the simple it said this. So things like, having a greater effective nuclear strength, we look at all of the things that can affect. Well, one of the things you need to think about that is related to this is how well two things stick together. So let's say we have, an ionic substance. That's a metal and a nonmetal. The metal is given up an electron to become a positive ion. The nonmetal is gained an electron and becomes a negative ion. You have oppositely charged things. That's a very strong attraction. Well, you need to remember there's implications to that. State being one, melting point, boiling point. So there's things we rarely touch on that can also apply to our ideas here. So ionic compounds, they're stuck together very strongly in that opposite attraction. So they're going to have very high melting points and very high boiling points, and they're going to likely be solids at room temperature. Molecules, on the other hand, the covalent situation is a much weaker attraction. So they're going to have lower melting points, lower boiling points. They're less likely to be a solid and more likely to be a liquid or a gas at room temperature. Now, there are other factors, which we're actually going to get into in future chapters, but just as a general rule, remember there's other places we can go besides, the exact things that we've looked at. So there's implications to all kinds of situations, and one of them is related to the whole ionic compound molecular idea, which is something we talked about last year a little bit. Next one, half-lives. Half-life problems, know how to do them, particularly when the amounts are given as a ratio of two isotopes. Because otherwise, in a normal problem, you're just using this equation, typically finding T. It's not too bad. You've got to find K, which means you got to know this equation. Remember, that's not on the AP constant sheet. But once you know K, you can plug that in. You can plug in this, and you can plug in this. And remember, this value is always larger than that value. So that's always a double check. Because remember, it decayed. You're going to start with more than you have now. So its mass is going to be greater. Its amount's going to be greater. Its number of disintegrations, it's going to be greater. So that's just a few general things about half-life problems. But the one you got to watch out for that sometimes throw people is when you have a ratio of two isotopes. That's because you have a hidden AT and A naught. So let's say the mass ratio of radium, or sorry, radon, no, radium, I started to say that right. Excuse me. Radium 226 to thorium 230 is 0.758. So we're talking about a ratio. Remember, it's hidden, but that means 7.58 to 1. So basically, which one of these is larger? Well, this one is, so that's what's decaying. So at the beginning, so I want to try and make this a little more concrete. This is supposed to be coming up. Well, I'll just have to draw it in then. So at the beginning here, and what's happening over time. So this block will represent my substance. At the beginning, we have 100% of our undecayed substance, which is thorium-230. So at the beginning here, this entire chunk is all thorium-230. So everything is thorium-230. And that's going to have some mass. Now, let's say my radium-226 is red in color. Well, after one half-life, remember half-life means half of it's gone, half of my substance has become radium-226, and the other half is still my thorium. So in this particular case, we would have a ratio of 1 to 1. So after one half-life, we're at a 1 to 1 ratio. And then if we went another half-life, so remember all of this had already converted. Now half of what's left is going to convert. Now that is what I've got. Well, in this particular situation, all I've got left is 0.25 of my original sample. If we're looking at 1, so this was 0.5, 0.5. That was our 1 to 1 ratio. At this point, we now have 0.75 to 0.25. So 0.75 to 0.25. When you divide that's going to be a 3 to 1 ratio. So if we're at one half-life, we're at 0.5. And as we keep going, this ratio is going to keep getting larger. Now, notice this number is in between those two. So we've gone through a little bit more than one half-life. How much more? Well, that's what we have to use the math to really try and figure out here. So that's conceptually what's going on in this situation. Now realize that these two things don't weigh the same. This weighed 230, and this weighed 226. So if we know that we have a 1 to 1 ratio, that means we had 1 milligram, let's say it was 1 to 1 milligram ratio, we had 1 milligram of the radium, and what we really need to know is how much thorium was that. So how many milligrams of thorium was represented by that? Well, if you don't want milligrams of radium and you want milligrams of thorium, or what you don't want to put on the bottom, what you want put on top, well, by the mass number ratio, for every 230 thorium, you only had 226 radium. So you can use this mass ratio to calculate how much more that is. It's going to be 1 point something or other. And what that's going to be able to figure out for me is, remember, if it's a 1 to 1 ratio, 1 to 1 of each, I already have 1 at time t, and I need to add what I get here. So I'm going to end up with 2 point something at the beginning if I did the calculation. Now, in the one that was actually given, it wasn't a 1 to 1 ratio. So the ratio that was given up here, it was 0.758 milligrams of radium. So when I go to do this one, it's the same idea. I don't want the milligrams of radium. What I want is the milligrams of thorium. And the ratio is 230 for every 226. So you would multiply this out. And in your calculator, if I pull up a calculator real quick, so 0.758 times 230 divided by 226, that gives me 0.771 to 3 sig figs. So that's how many milligrams of thorium I used to have. So that means I'm now at 1. So that's my AT. And I used to be 1.771, because remember you have to add that to 1. That's going to be my A naught. And remember, this is exactly 1, so think of it as 1.00 forever. So that's how you would do one of these types of problems, because now that I've got that, I can plug this in there, I can plug this in there, and they would have given me the half-life, so I could have solved for K and plug that in there, and I got T. Next idea, writing nuclear decay reactions. Just a couple quick things about this. So first quick, write the balanced nuclear reaction for the alpha decay of uranium-238. Remember, if it's a decay of uranium-238, that's what I'm starting with. If it's an alpha decay, one of my products will be an alpha particle, which is a 4/2 He. Remember, you need to know alpha particle, electron, which is 0/-1e, positron, which is 0/1e, and you also need to know a neutron is 1/0n. So those are four subatomic or four types of particles you need to know. These three are a decay particle type situation, but you also should understand what neutron is. If you got a 1/0, it's a neutron. So the key idea here is what's on top, mass number has to equal on both sides. So on top I need a 234, and what's on bottom has to equal. So on bottom, so on top, I've got to have a 234 because 4 plus what equals 238? And on the bottom, 2 plus what equals 92? That's got to be 90. And then next, check your periodic table. Because remember, the periodic table is going to show you what atomic number is what. You don't need to memorize them. You just need to look them up. And if you look up in the periodic table, number 90 is pH. So that would be the answer to the first one. Now, what happens if it says in my question, what if this product then undergoes a beta decay? So what's my product here? Well, that's my product. So that's going to be my starting point in the next step. Well, it's undergoing a beta decay, so that means I'm going to be releasing a beta particle, which is that one. So that's got to be one of my products. And the question is, what am I missing? Well, remember, on top has to equal, so that's got to be 234. On bottom, -1 plus what equals 90? Well, that would be 91. Same thing, look on your periodic table. If you look up 91, that's Pa. So remember, you can undergo subsequent reactions. So first it underwent an alpha, and then that underwent a beta. Another situation, what happens if we have a reaction where it's not a decay reaction. So this is a reaction where I'm bombarding uranium-235 with a neutron. What happens there? Well, I'm going to end up getting products. What would be my missing product? So what's going to be my question mark here? Well, the same thing applies. Remember, what's on top has to equal, but you got to be careful of this 3. If we have 3 neutrons, that really means we have 3/0 here. So instead of 142, plus 1, we have 142 plus 5. So the total on the left side is going to be 236 on top, and the total on the left side is going to be 92 on the bottom. Well, on top, I've got 142 plus 3, 145. And on the bottom, I have 56 plus 0. So that's going to be 56. So 145 plus what equals 236? So 236 minus 145 is going to equal 91. So my missing mass number is 91. 92 minus 56 equals what? Well, 56 plus 36 equals 92. So my missing substance here is element number 36. So what's my missing substance? Krypton. So that was my missing particle in this reaction. And that ends my chapter help for the chapter 6, 7, 21 test.